Okay, welcome back. Today we're going to cover chapter 17, velocity of sound, and then we're going to cover the theory about it. And then so we see here the three equations. Velocity of sound in air is 331.4, square root of the temperature of the air divided by 273. And then velocity of sound in solids, which is equal to square root of, this is called the Young's modulus of the solid, Young's modulus, divided by the density of the solid. And then velocity of sound in liquids and gases is equal to the square root of the bulk modulus. Bulk modulus. So today we will go over this, explain them, and then try to make sense of what they mean, and also give some examples of different materials with different Young's modulus, bulk modulus, and different temperatures of the air. So you will get acquainted with these equations. So what is this one saying? This one is saying that the velocity of sound in air is 331.4, this is already in units of meters per second. Then square root of the temperature, this temperature is in Kelvin over 273. So let's see what that means. If the temperature in Kelvin is 0 Kelvin, right, this is absolute zero, that means that's the temperature at which all molecular motion has stopped. Well, this is saying then the velocity of sound will be 0, right, meters per second. So this should make sense because when molecular motion has stopped, sound waves cannot propagate through the medium because a sound wave is the propagation of the vibration of the molecules and the propagation of the energy of those molecules. So if the molecules aren't vibrating in the first place, then they should not be traveling, right? So then if the temperature is 273 Kelvin, which is equal to 0 degrees Celsius, right? Then we can put here 273 over 273, and then you get square root of 1. And then so velocity of sound at 0 degrees Celsius is going to be 331.4 meters per second. And if we convert that to miles per hour, we see that it's equal to roughly 745.6 miles per hour, right? And then the velocity of, and if the temperature is equal to 293 Kelvin, which is 20 degrees Celsius, so that's a typical room temperature. So then we can put here 293, velocity of sound at 293. Then you're going to get 331.4 square root of 293 over 273. Then when we put that in, we get 343.3 meters per second. This is usually the velocity of sound that we're going to assume for most problems. If the problem doesn't tell you the temperature of the air, then assume that the temperature of the air is 20 degrees Celsius, and you can use the 343.3 meters per second. That's for, unless the problem tells you the temperature is something else, then you would have to calculate what the velocity of sound in that area is, right? So this is the default velocity of sound. And then this gives you 772.4 miles per hour. Okay, and then as the temperature gets bigger and bigger, there's a square root relationship here. So you see here that the velocity of sound as a function of temperature, when the temperature is 0 Kelvin, then the velocity of sound is, this is meter per second. It starts at 0, then it increases as a square root. So I'll also try to make sense of why it should be a square root relationship, why there is that square root relationship. So the farther the temperature in the air, the faster the air molecules are moving, and therefore they should be able to propagate the energy of sound waves quicker. But why should it be a square root relationship? Why shouldn't it be just a linear relationship? Why shouldn't it be a square root relationship? So I'll try to make sense of that also. You might have heard of the term Mach 1. Mach 1, let me just explain that quickly. That's when a spacecraft or any kind of airplane or anything, that it goes at the speed of sound. So if the temperature in the air is 20 degrees Celsius, then Mach 1 would be equal to 343.3 meters per second if the temperature is 20 degrees Celsius, right? But let's say the aircraft is flying at a very high elevation, the temperature is not going to be 20 degrees Celsius. Maybe the temperature is 0 degrees Celsius, right? So if the temperature is 0 degrees Celsius, then Mach 1 would be 331.4 meters per second. So there is no such speed as you can say, what's Mach 1? What does that mean? Well, it depends on what the velocity in the air is. The cooler the air, the velocity in the air is going to be slower, then the Mach 1 speed is going to go down. So as long as you're going at the speed of sound for that temperature, depending on what the temperature is, then you are going at Mach 1. If you're going Mach 2, then you're going twice that speed. Mach 3, 3 times that speed, and so on and so forth, 4, 5, 6, 7. Okay? So let me explain why the square root relationship comes about. We will see later on in the course, when we cover in chapter 21 the Maxwell distribution of gas speeds, we're going to cover this equation, 1/2 mv squared average is equal to 3/2 kT. So this is going to be later on in the course, and then we're going to define something known as, so the 2 and the 2 cancels, 3 kT over m. Then we're going to define something known as V root mean square. V root mean square, and that's going to be equal to the square root of V squared average, and then that's going to be equal to square root of 3 kT. In other words, the most important speed that a gas molecule can go at is not its average speed, and it's not its most probable speed, right? So I'll explain that more in detail when we get to that chapter. It's known as the most important speed is known as the root mean square speed. It's the square root of the 3 times the Boltzmann's constant times the temperature of the gas divided by the mass, right? So this makes sense then if the velocity of the molecules is dependent on the square root of the temperature of the air, then the velocity of a sound wave in that gas, right, should depend on the square root of the temperature too, right? Because the hotter the air temperature is, the faster the air molecules are moving, and the faster the air molecules are moving, proportional to the square root of the temperature, and therefore the propagation of sound energy through that medium should also be proportional to the square root of the temperature of that medium, right? So that makes kind of sense of the square root relationship. Okay, I believe that is all for in terms of the explaining the theory behind the velocity of sound in air. Let's go to the velocity of sound in solids. So let's say you have a rod like this, and I exert a certain force in one direction, right? And I'm trying to stretch the rod, and then this is the area of the rod, right? So what we do is we say the Young's modulus of y is defined as the force that you apply divided by the surface area here, divided by the resulting change in length of the rod. So remember, the rod has a certain length here, L, and then maybe as a result of applying that force, the length of the rod is going to increase by a certain amount, delta L. So you divide delta L over L. So divide by the resulting change in length of the rod, divided by the length of the rod. So this is meters over meter, so that cancels. And then this is force over area, so that's going to be Newton per meter squared, which is going to be pascals. So Young's modulus is measured in pascals. The greater the value of the Young's modulus, that means you need more force per unit area to cause the same change in length divided by the original length, right? So the greater the y, the greater force you need. That means it's harder to stretch. So what does that mean? Well, if the greater the y, that means the molecular bonding of the molecules in that solid is much stronger. They are tightly bound. So when you try to stretch them, they don't want to stretch easily, right? So does that make sense that the greater the Young's modulus, the greater the velocity of the sound wave in that medium, right? Let's think about that. If the molecules of that medium, right, are tightly bound, when the left ones begin moving, let's say these ones begin moving, right and left, then the ones on the right start feeling it much more quicker, right? So that's basically what a sound wave is. You bang on one side of the rod, rod, and you begin this molecular motion on one side of the rod, right? And the faster that molecular motion energy travels through, then the greater the velocity of the sound wave, right? So if the bonding of the molecules is much stronger, it makes sense that the molecular motion on one side will travel across much quicker, right? So that really kind of makes sense. I'll give you a little analogy, to a human analogy. Just say a rumor begins among a group of friends, right? A rumor begins, and let's say there's a group of 100 friends. If those 100 friends already usually text each other and call each other every day or every couple of days, the rumor will spread quicker through those group of friends, right? If they don't talk to each other and they don't text each other too much, then the rumor will not spread. It might take a month for it to spread through all of those 100 friends, right? So the more stronger they are bound together, the faster that rumor will spread. Well, same idea here with the velocity of the sound. How about this bottom one, density? This rho is measured in kilogram per cubic meter. Well, that's the same density that we've talked about before, right? That means the molecules weigh more. So what does this mean? The smaller the density, the bigger the velocity of the sound. So you want the molecules to not weigh that much. Well, does that make sense? That one is pretty much makes sense, because if they are very light, they're going to move faster, right? If they are heavier, they're not going to move as fast. Well, just like this equation says, root mean square velocity of gases is 3 kT over m. The bigger the mass, the less the velocity will be, right? The smaller the mass, the bigger the velocity will be, right? This applies for gases, but the same idea will hold true for solids and liquids, right? The smaller the mass, they will move faster. So let's now see if the units of this work out to give you meters per second. So let's do some unit analysis. Okay, so this one is in pascals, we already said, the Young's modulus, and this one is kilogram per cubic meter. And then we're going to take square root of that. So unit analysis is a good way to sometimes check formulas and to make sense of them and see if the units work out. Pascals is equal to Newton per meter squared. Okay, and then you get Newton per meter squared times meter cubed over kilogram, right? Multiplied by the reciprocal of that. Then you're going to do square root of, and then one of the meters cancels, right? Then you're going to put down what the definition of a Newton is. A Newton is a kilogram times a meter per second squared. Then you're going to multiply that by a meter per kilogram. Kilogram cancels the kilogram. Then you get meter squared over second squared. Square root of meter squared over second squared is equal to meter per second. Not bad, huh? A little bit of unit analysis shows that the units of that work out to be true. Okay, now let's give some examples of different materials. The Young's modulus of steel is 20 times 10 to the 10 pascals. These are usually big numbers. Young's modulus of copper is equal to 11 times 10 to the 10 pascals. Young's modulus of aluminum, 7 times 10 to the 10 pascal. You can see this makes sense because usually steel, we consider that to be much harder to stretch or compress. Copper is a little bit easier to stretch or compress, and aluminum is even more pliable, right? Easier to stretch and compress. So 20, 11, 7. Glass is equal to, depending on the type of glass, 6.5 to 7.8 times 10 to the 10 pascals. And then tungsten is equal to 35 times 10 to the 10 pascals. And then wood, of course, it also depends on the kind of wood. 0.3 times 10 to the 9th pascal. So notice that it is one order of power less. Or we can change this to 10 to the 10th and say 1.13 times 10 to the 10th pascal. So these are 20, 11, 7, 6, 35. This goes all the way down to 1. So it should be much easier to stretch wood or to compress wood. Okay, so that makes sense too. So steel, the metals are usually harder. So now let's actually calculate the velocity of sound in a couple of materials and compare them. In steel, square root of 20 times 10 to the 10th. So we're going to take this number. Then I'm going to divide that by the density of steel. which is 8,050. Notice that I am using, for the density of steel, I'm using the kilogram per cubic meter version, 8,050. In gram per cubic centimeter, it would be 8.05. But you shouldn't do that when you're doing this. You should stay in metric unit system. So then when you do that, you're going to get 4,984.4 meters per second, 11,215 mile per hour. That is very, very fast. So you bang on steel on one end, that velocity of sound travels very quickly to the other end, 4,984.4. So much, much faster than the velocity of sound in air. Remember, at 20 degrees Celsius, the velocity of sound in air was 343 meters per second. So this is in the order of 5,000. Okay, how about the velocity of sound in aluminum? Square root of 7 times 10 to the 10th, right? Divided by what? Well, the density of aluminum is going to be smaller than the density of steel, 2,700. So notice that even though the Young's modulus of aluminum is smaller, right, than the Young's modulus of steel, the density is also smaller. So actually velocity of sound in aluminum might be faster because these two things are competing against each other, right? So when you do this, it actually does come out faster. 5,091.7 meters per second. So how about the velocity of sound in wood? Square root of, let's just round this to, of course it depends on the kind of wood, let's say 1.1 times 10 to the 10th, right? Divide this by the density of wood. Well, it also depends on what kind of wood it is. Let's say the wood is about 70% as dense as the water, so its density will be 700. 700, remember the density of water is 1,000 kilogram per cubic meter, so if the density of the wood is 70% of the density of water, it'll be 700. So so once we put all of this in, we get 3,964.1 meters per second. So even though this was less than this, and this also was less than this, but this one was much less than this compared to this and this ratio, right? So even though they were both less, this one, the top one was more or less. So the velocity of the sound in wood did come out smaller than either of these, but it's still much faster than the velocity of sound in air, okay? Now let's cover the velocity of sound in liquids and gases. You don't have to do the unit analysis again because bulk modulus is also measured in pascals and density is the same thing, so we can see that the units do work out. Let's just explain what the bulk modulus is and then also give some examples. So imagine that there's a three-dimensional shape here, a liquid or a gas, and then now we exert a certain force on it, and then this is A. So it's going to be the same idea, but now we're applying it to a three-dimensional volume. So we're going to say the bulk modulus is defined as the force over the area divided by delta V over V. So the resulting change in volume of the gas or the resulting change of volume of the liquid, right? Instead of the resulting change of length. So that's the only difference. So then you're still going to get here Newton per meter squared, and then on the bottom you have meter cubed over meter cubed, which is unitless, so it's still going to be pascals. So what is the bulk modulus measuring? It's measuring how hard it is to compress the liquid or to expand the liquid. Instead of using the word stretch, because stretch is more a one-dimensional term, and so we can use that for solids, right? So for liquids and gases, we're going to say bulk modulus measures how hard it is to compress it or to expand it, make it three-dimensionally larger, right? So of course, the bigger the bulk modulus, the more force it's going to take to compress it or to expand it, and therefore the same idea holds. If it takes more force, that means the molecular bonding is stronger, that means the velocity of sound should be larger through that medium. So same idea as for solids, right? So now let's give the bulk modulus for different materials. So we're going to do water, the bulk modulus of water, 2.1 times 10 to the 9 pascals. And then the bulk modulus of mercury is going to be 2.8 times 10 to the 10 pascals. And then, so you can see here, the mercury is much more tightly bound. It's much harder to compress or to expand it, right? So it's a tenth of an order greater than the waters. Then we can have bulk modulus of air is an example of a gas. It's going to be 1.42 times 10 to the 5th pascals. That's if we try to expand the air adiabatically. Which means no heat exchange between it and the surrounding. And then the bulk modulus of air is 1.61 times 10 to the 5th Pascal. And that's if we try to expand or compress it isothermally. And then isothermally means the temperature is constant. So this means no heat exchange. Okay. So now let's apply this and then find out the actual velocity of sound in some mediums. Okay. We're going to get 1,449.1 meter per second. So around 1,500. You can see that the velocity of sound in liquid is much faster than the velocity of sound in air, but it is still slower than the velocity of sound in a solid, right? So that makes sense. In a solid, it should propagate faster because the molecules are more tightly bound. Okay? So now let's calculate the velocity of sound in mercury. Velocity of sound in mercury. Well, the bulk modulus of mercury was bigger, right? It was 2.8 times 10 to the 10th. And divide that by the density of mercury. Well, the density of mercury is 13.6 times denser than water. It's very dense. So we have 13,600 kilogram per cubic meter, right? So when you do that, well, this is bigger than this, but this is also bigger than this. So it actually comes out to be about the same, but it actually comes out a little smaller than the velocity of sound in water, right? Because the density was quite a bit larger, right? Interestingly, what would the velocity of sound in air be if we use this equation, right? So velocity of sound in air, let's say we use the bulk modulus of air divided by the density of air, right? The bulk modulus of air, we said, was around what? Well, depending on what kind of process it is. So let's use the adiabatic, 1.42 times 10 to the 5th, right? And then the density of air is 1.29 kilogram per cubic meter. So of course it depends on the temperature of the air, because the temperature of the air is going to affect its density. And the temperature of the air will also probably affect the bulk modulus of the air. So right now, we don't really see the temperature dependence of this equation. Remember, the other equation was 331.4 square root of the temperature over 273. That one literally told us the temperature dependence of the velocity of sound in air. This one we don't really see because this seems like it's a constant, this seems like it's a constant. The modulus and the density are actually temperature dependent, so we don't really see that here. But let's just see what kind of a ballpark answer we would get. When you put this all in, and it gives you 331.8. 331.8 meters per second. So it actually gives you a ballpark answer similar to the one that we got when we actually used the literal temperature dependence of the velocity of sound in air. So it means that both of them are agreeing. Okay, but from now on, the velocity of sound in air will use the other equation because that literally has the temperature dependence. But we can see from here that the two of them actually match. Okay, concluded, and we've covered the topics of the velocity of sound in air, solids, and liquids and gases. Okay, thank you very much.